What is the hottest temperature in the known universe? From what we know about our universe, the coldest possible temperature is absolute 0 degrees Kelvin, or minus 273.15 degrees Celsius, minus 459.67 degrees Fahrenheit. But what about the hottest possible temperature? Physics is a little fuzzy on what the absolute hottest of hot looks like, but theoretically speaking, such a thing does, or at least, did, once exist. It's called the Planck temperature, but, as with everything in life, it's also not that simple. What is temperature, anyway? First thing that might come to mind when thinking about temperature might be a description of the amount of heat an object contains. Or, for that matter, doesn't contain. Heat, or thermal energy, is an important part of the explanation. Our intuitive understanding of heat is that it flows from sources with higher temperatures to those with lower temperatures, like a steaming cup of tea cooling as we blow on it. In physics terms, thermal energy is more like an averaging of random movements in a system, usually among particles such as atoms and molecules. Put two objects with varying amounts of thermal energy close enough to touch, and the random movements will combine until both objects are in equilibrium. As a form of energy, heat is measured in units of joules. Temperature, on the other hand, describes the energy transfer from hotter to colder regions, at least theoretically. It's typically described as a scale, in units like Kelvin, Celsius, or Fahrenheit. A candle's flame might have a high temperature compared with an iceberg, but the amount of thermal energy in its heated wick isn't going to make much of a difference when placed against the mountain of frozen water. What exactly is absolute zero, then? Absolute zero is a temperature, so it's a measure of the relative transfer of thermal energy. In theory, it marks a point on a temperature scale where no more thermal energy can be removed from a system, thanks to the laws of thermodynamics. Practically speaking, this precise point is forever out of reach. But we can get tantalizingly close. All we need are ways to decrease the average amount of thermal energy spread among the particles of a system, perhaps with the help of lasers, or the right kind of flip-flopping magnetic field. But in the end, there is always an averaging out of energy that will leave the temperature a fraction above the theoretical limit of what can be extracted. What is the hottest temperature possible? If absolute zero sets a limit on pulling thermal energy from a system, it might stand to reason there's also a limit to how much thermal energy we can shove into one. There is. In fact, there are a couple of limits, depending on precisely what kind of system we're talking about. At one extreme is something called Planck temperature, and is equivalent to 1.417 x 1032 Kelvin, or something like 141 million degrees. This is what people will often refer to as the absolute hot. Nothing in today's universe comes close to these kinds of temperatures, but it did exist for a brief moment right at the dawn of time. In that fraction of a second, a single unit of Planck time, in fact, when the size of the universe was just one Planck length across, the random movement of its contents was about as extreme as it could get. Any hotter, and forces like electromagnetism in the nuclear forces would be on par with the force of gravity. Explaining what this looks like demands physics we don't have a grip on yet, one that unites what we know about quantum mechanics with Einstein's general theory of relativity. Those are also some pretty specific conditions. Time and space will never be so confined again. Today the best the universe can manage is the paltry few trillion degrees we create when we smash atoms together in a collider. The opposite of absolute zero. But there is another way to look at heat, one that turns the whole question of temperature on its head. Keep in mind that thermal energy describes an average of movements among the parts of a system. All it takes is a small percentage of its particles to be flying about chaotically to qualify as hot. So what happens if we flip this state and have far more zippy particles than sluggish ones? It's what physicists call an inverted Maxwell-Boltzmann distribution, and weirdly, it's described using values that go below absolute zero. This strange system seems to throw out the rulebook on physics. Not only do we quantify it as a negative to absolute zero, it's technically hotter than any positive value. Quite literally hotter than hot. As a quirk of statistics, it's not something we'd find in any natural corner of the universe. For one thing, it'd require an infinite amount of energy, and then some. That doesn't mean we can't bend the rules a little and make something like it. In 2013 it was demonstrated by physicists at the Ludwig Maximilians University Munich and the Max Planck Institute of Quantum Optics in Germany. They used atomic gases within very specific settings though, which impose their own upper energy limits. The results were a stable system of particles with so much kinetic energy, it became impossible to shove any more in. The only way to describe this particular arrangement was by using a temperature scale that went into negative Kelvin, or several billionths of a degree below absolute zero. Such a bizarre state could in theory absorb thermal energy not just from hotter spaces, but from colder ones as well, making it a true monster of extreme temperatures. In this diabolical corner of the universe, a machine would be able to chug away at greater than 100% efficiency as it fed from hot and cold alike, seeming to thumb its nose at the laws of thermodynamics. Let us know your thought on this in the comment box.
For daily video updates, subscribe to Only Facts.